Hey, how's it going, everybody? Before I get started, I want to say thank you. I just checked the account. It's at 1,000 subscribers. Well, a little bit more, right? Appreciate all the support. I've been seeing the comments. All the help you guys been pretty much obtaining from my videos. For those that don't know, right, I started making these videos for my sister, who's planning on becoming a ME major down the line. Well, actually, hold on, next year. She's graduating high school this year, so damn, next year already. Um, Pretty much I'm trying to make these videos before I forget them. So hopefully down the line she won't have to ask me for help because that's what she's been doing lately for calc. And you know what? Calculus, it's been so damn long. I have no idea what even goes on there anymore. But um and I mean at work, been busy too, guys. I apologize. I've been trying to make more videos, but work, I'm putting in 50-hour weeks, and then I'm going to school too for my master's, so that's cool. I finally found some time today. I'm like, you know what? Enough's enough. So here I am. Let's go ahead and get started, right? For this question, with this problem, we're gonna determine rotation at pin A, rotation and displacement under load P, and we're pretty much just gonna draw the shear and bending for beams, right? For beams, there's only transverse loads. Not really only, but the transverse loads are so huge that axial and torsional effects are neglected. So in these problems not moving forward, just for this chapter, we're going to be focused on finding displacements in the y direction and moments. So no axial effects, so nothing in the x direction. So that should make our lives pretty easier. We're going back to just 2 by 2, well, two, how should I say this? A 4 by 4 matrix. Previously, we were doing 6 by 6, right? At the very end of that other chapter. I can't remember what it was. But yeah, in this case, we're going to determine all these. And you know what? Let's go ahead and get started. All right, guys. So for this chapter, this is going to be our stiffness formulas, you would say, right? For K, just like we've seen in other chapters for springs. And I forgot what the other chapter was. It's been a while. But in this case, we're doing the EI over L cubed multiplied by this matrix right here. It's between two nodes, right? You'll have technically, between nodes 1 and 2, you'll probably have V1, Phi1, V2, Phi2, and so on. So it's a little 4 by 4 for every beam element. In this case, we have two beams, so we're gonna have a 6 by 6. I'm sorry, right? Three nodes to the y displacement and the rotation for each node. But before we start doing that, right, this is going to be, let's say, the first step right here. We're going to start with the boundary conditions. So, like, let me write that down. In FEA, this is one of the biggest things, right? You should know how to do this. This is really going to make or break your problem. This is more of a statics machine design kind of thing. If you're taking FEA, I'm assuming you have a lot of background with this kind of stuff. So for every node, let's go ahead and label the nodes, right? We're going to have node 1, node 2, node 3. We're going to have V1 is equal to Phi1 is equal to V2, Phi2, and V3, Phi3. All right, this right here is a pin, so it can rotate, but it's not moving in the y direction up or down. So that's going to be 0 for displacement for V1. It's a pin, right? So when you apply this force here, there's going to be some rotation. We don't know what that's going to be, but it's going to have an angle to it. So we're going to put here question mark, right? We're looking for it. For V2, Phi2, when you apply the force here, you're going to displace it down, so we don't know what that number is, and we're going to have an angle to it, right? Like I said, this is all just review from statics. It's fixed here at node 3, so it's not moving no matter how much force you put anywhere, and it also isn't going to have an angle, so that's also going to be 0 right there. And previously in the other videos, I'll do the K element for each one, for each beam, right, or for each spring, whatever, but in this case, we're doing the beam equation, so I'm assuming you already know what's going on. So I'll just go ahead and start assembling the whole global stiffness equation. Global, whatever it's called. It's been a while. And the reason we could go ahead and add them up between, we we could assemble a huge matrix is because they all share the same properties, EI over L cubed. If this wasn't the same length as this, then no, we wouldn't go ahead and start summing it up in the huge matrix, right? We'd have to pretty much have all these on the outside identical prior to adding. If you've seen the other videos, you know what I'm talking about. And like I said, if you're already in this chapter, then that means you know what I'm talking about. So in this case, right, they all share the same EI, so we'll go ahead and do that. EI over L cubed. Let's go ahead and do the first beam. So it goes from nodes 1 to 2. So V1, Phi1, V2, Phi2, V1, Phi1, V2, Phi2, right? In this case, it's just this formula right here, this stiffness matrix. So we're going to go ahead and put 12, 4L squared, 12, and 4L squared. These are going to change in a bit, but let's just go ahead and do it as one first. Right, 6L. Let's do negative 12, 6L, negative 6L, 2L squared, negative 6L, and it's symmetrical, so all the rows become columns. 6L, negative 12, 6L, right? This row became this column. Same thing here, negative 6L, 2L squared, and negative 6L. Another thing I forgot to mention real quick, to make this easier, right, because they give us no numbers, and it's going to be a mess, you'll see in a bit, but let's go ahead and assume, well, not assume, let's just kind of give it the place value. Let's give it L is equal to L over 2, okay? Because if we start doing that, then we got to start dividing it inside, and it becomes a mess. So let's do it at the very end, and for now, let's just play with an L. Assume it's just to make it neater. All right, so that was that one, right? It was between nodes 1 and 2, so it falls into the 1 to 2. Now this one falls between 2 and 3, so we're going to pretty much go from 2 to 3, 2 to 3, right? So let's go ahead and do that. 12 will get added to this 12 right here, so this becomes a 24. 6L will be added to this negative 6L. And it'll also be added to this one right here. So that's going to be a 0, 0. Then 4L squared plus 4L squared right here. That's going to be 8L squared. All right. And then everything else is pretty much the same, right? Negative 12, 6L. Okay. Then we got negative 6L and 2L squared. My bad, guys, I don't want to mess up. Make sure I'm going a little bit slower, but just to make sure I'm going good. Yeah, seems right? So the rows become columns. Negative 12, 6L, negative 6L, 2L squared, negative 6L. There you go. And then whatever's vacant is just 0. So this chapter, I mean, nothing crazy. If you know how to do the last one, you know how to do this one. It's just working with displacements and moments instead of the X and Y's. It's pretty much just that. So yeah, let's go ahead and continue. What's next? Let's apply the boundary conditions to the global equation. So we have V1's equal to 0, V3, and Phi3. And we apply them here, pretty much. Nothing crazy, just like we've always been doing, right? 0, 0, 0. And like I said in other videos, right? But I'll say it again. When you know your boundary conditions, you don't know your forces or moments, in this case too, right? And where you know your forces, you don't know your boundary conditions. So that's a cool kind of a trick to know. Okay, it applies to the whole class, I remember. And I mean, it's something you should know, right? Like I said, it's something important in FEA. So in this case, what I'm trying to say is, since we know displacement 0 here, displacement 0 here, and the angle shift is angle here, 0 here, then that means we don't know these 1, 2, and 3, that one right there. So that means we should know these. So just by observation, right, we see that there is at pin A, there is, oh no, that's going to be a force, right? Because it's displacing, so we don't know it. We don't know this one, so we should know this one. It should be 0. it's a pin. It's gonna rotate however you, I mean, what I'm trying to say is if you put a force here, it's just gonna, all right, let's move this way. All right, let's move up if you're applying it upwards, right? That's all it's saying. There's no reaction for moment there. F2y, we see it's negative p. Again, right? Let's assume y, and then this way is positive. Positive. I'm just saying counterclockwise is positive for a moment, and then in the up direction is positive for a y. In this case, we have negative p, right? Cool. M2, we see by observation that there is nothing being applied, so that's also 0. So cool. We applied 6 conditions, right? 3 boundary conditions and 3 loads. So now we could go ahead and start assembling the equation. We always focus on the ones we don't know. So in this case, these 3 equations right here, phi1, v2, and phi2, and where you know your forces and moments. So in this case, we're gonna have the first, it's gonna be, let's put 0 is equal to EI over L cubed, but I'm gonna divide EI over L cubed to this side. And when you divide 0 by this, you get 0. Okay, so this goes away. So let's focus on that second row. It's gonna be 6L times 0 plus 4L squared phi1. So we're gonna put 4L squared phi1 minus 6LV2 minus 6LV2, then plus 2L squared phi2 plus 2L squared phi2, and then 0V3 plus 0 phi3. Cool, so that one's done. Let's do the next one. Negative P, divide this by both sides, so you'll get negative P L cubed over EI is equal to, let's go ahead, we're in this row right here. It's easy to get confused. We're in the third row, so right here. Negative 6L. The reason I'm focusing on these 3 is because all these are 0. So it doesn't matter what this is, this or this, okay? So negative 6L phi1. Okay, we're gonna put 24V2. And then plus 0 phi2. So we'll just put plus 0. Then finally, we'll do the third one, which is the fourth row. So 0, same thing, right? Divide both sides by EI over L cubed. 0 is equal to 2L phi1. 2L phi1. What else? What else? 0 V2. So plus 0 plus 8L squared phi2. And there we go. We got 3 equations, 3 unknowns. So we could solve it. It's going to take a little bit of algebra. And 1 right there. So here are the answers. V2 is equal to negative 7PL cubed over 96 EI. Phi1 is equal to negative PL squared over 8 EI. I'm sorry, did I say phi squared? Phi1. And phi2 is equal to PL squared over 32 EI. Now, I'll show you how I got these, right? But I just wanted to save space and time because it's a lot of algebra. And it's not really FEA, so it kind of makes no sense to spend so much time on it. But look, here's what went down. So we were here, right? We got the 3 equations. I already did this beforehand. So here are the 3 equations that we just got. And I stuck, right? Like I said, it's just algebra at this point, but this is what I did. So I stuck with equations 1 and 3. You're going to have to use all 3, so don't think you're going to have to avoid a complicated one because you're going to have to end up using all of them at the end, okay? So in this case, I did 1 and 3. I wrote down both of them right here. So 0 is equal to 4L squared phi1 minus 6LV2 plus 2L squared phi2. And then I got the third one. 0 is equal to 2L squared phi1 plus 0 plus 8L squared phi2. And just like you would in algebra, right? 3 equations, 3 unknown system of equations, that topic. I multiplied the top by negative 4, and I was able to cancel this 8L squared. So boom, at that point we had two equations and 2 unknowns here. So I did that, right? Multiplied all the top by negative 4, and I got this right here up top. Then the bottom stayed the same. The second equation stayed the same. Then you add them. So negative 16 plus 2, that became negative 14. 24 plus 0 became 24 LV2 right here. And then this went away. So what I did was I moved it to the other side. And I mean, here's a whole solution if you want to pause it here, but just continuing to write what's going on. 14L squared phi1 is equal to 24L v2. So phi1, you find a relationship for phi1. It's equal to that right here. Then you use equation 2, which was this right here. I use that phi1 and I plug it in. Okay, equation 2 is this one right here. Okay, and then plug in phi1 for this, and you solve for v2 in this case, right? Because phi1 is in terms of v2 here. So you'll have everything in terms of v2, right? v2, v2. Then at the end you get this. v2 is equal to -7 pl cubed over 96i. Now, it's not our final answer yet, because technically this is what the problem's asking for. But remember, we did the L over 2 substitution, so we have to account for that. But let's do it at the end. Just hold off. You find v2. Then, from step 6 in this case, right, which was this one right here, phi1 is equal to 12 v2 over 7L. You plug in. In this case, you found your v2 already. So it's this. You plug this into this, and you find your phi1. Phi1 is equal to -pl squared over 80i. Then from equation 3, it was this, right? 2L squared phi1 plus 8L squared phi2. In this case, you already found phi1 in terms of pl and ei. So in this case, you could find phi2. So when you do that, you get this right here. Phi2 is equal to pl squared over 32 ei. So that's what went on right over here. So we could go ahead and continue. In this case, we could go ahead and set, now that we found our 3 boundary conditions, right, the ones that we didn't know, which are these 3, let's go ahead and find f1y, f3y, and m3. So let's assemble the equations, right, just like we would normally. Let me put some steps here. So step 1 was boundary conditions. Step 2 was the global equation. Step 3 was assembling the equations itself. And step 4 was finding the v2, phi1, and v2. So step 5, we're going to call this finding, I don't know, right? Unknown forces, unknown F's, M's, forces and moments, okay? So in this case, right, force 1y is equal to, let's go ahead and assemble it. F1y is the first row. It's equal to 6L phi1, right? Because 12 times 0 is that, oh, you know what? Hold on. EI over L cubed. Can't forget about that. That's huge. Okay. 6L phi1 minus 12, all that good stuff, right? So 6L phi1 minus 12 v2 minus 12 v2 plus 6L phi2 plus 6L v2. All right. F3y, same thing, right? EI over L cubed. We're going to have this equation right here. So -12 v2. So -12 v2 minus 6L phi2 minus 6L phi2. And that's it, right? Just want to make sure we're good. 0, 0, -12, -6, L, 0, 0. Yeah, we're good. There you go. And then finally, M3y is equal to EI over L cubed. And it's going to be 6L v2, 2L squared phi2. Okay. And 6L v2 plus 2L squared phi2. Okay, cool. So we got 3 equations, 3 unknowns again. And if you solve for them, again, I'll show you guys in a bit, but F3y will equal, I'm sorry, F1y. F1y will equal 5 over 16p. F3y will equal, what's that going to be? 11 over 16p. And then finally, M3. Yeah, I'm sorry, this isn't M3y, this is just M3. There you go. M3 is equal to -3 LP over 8. There you go. So let's cloud these. Again, these aren't our final answers. We have to account for the L substitution right here. Okay. So I like to cloud them when it's not final, but it is important. All right. So let's kind of run through it real quick. Same thing, right? We assembled the equations. F3y, for some reason I did that one first. I don't know why. But EI over L cubed, -12, plug in your V2 that you found here, right? And right here. And then V2 goes into this. I'm sorry, this V2 goes into this. -6L, V2 goes into here. Do your algebra right. At the end, it cancels out nicely. Everything could have the L cubed over EI, and that's what cancels out. So everything cancels out pretty nice. Just FYI, look, so EI cancels out with both of them, and L cubed cancels out with both of them on top. You get F3y is equal to 11 over 16p. Now verify all these answers. Just FYI, they're correct. So if you did get something wrong, you might want to double check your algebra. But these are correct. Same thing for M3, right? EI, then plug in your V2. So the equation's up here, what's going on down here. 2L squared V2 right here. Okay. And like I said, EI over L cubed cancels out on the inverse inside the parentheses. So at the end, you'll get M3 is equal to -3 LP over 8. Finally, F12, right? EI over L cubed, plug in, do your thing. Or in this case, right, I'll just guide you guys. Phi1 gets plugged in. Right there, you guys could see. Phi1 gets plugged into here. V2 gets plugged into this one. Then Phi2 gets plugged into this one. Find a common denominator, right? So you can add them. Then you get F1y is equal to 5 over 16p. Now, let's go ahead and account for the L squared. Shouldn't be anything crazy, right? In this case, let's go ahead and put step 6. Should we put it here? Yeah, let's put it here, just so you can have it on the same page. Step 6. Remember, I like to do this, right? Remember, L is equal to L over 2. So that means V2 is equal to -7PL cubed over 768 EI. So in this case, right, your L, when you plug in L over 2 cubed, you get L cubed over 8. So 8 gets multiplied to 96. That's how you get that 768 right there. Phi1, same thing, right? This one, in this case, it's squared. So you'll multiply 8 times 4, right? Because L squared, sorry, L over 2 squared is L squared over 4. So you'll get that over 32 in this case. So -P L squared over 32 EI. Phi2, what's that going to be? Same thing, L squared, so you multiply the bottom by 4. So you'll have PL squared over, what is that? 120. Oh, wow. Got it wrong on this paper. 32 times 4, that's 64. And then times 2, that's 128. 128 EI. Oh, man. Got to fix it on the other paper. But it's 128 over EI. I mean, PL squared over 128 EI. F1y, what is that? In this case, it's independent of L. So it stays the same, 5 over 16p. F3y, it's also independent of L, so it becomes 11 over 16p. Then M3 is L over 2, so that's -3 LP over 16. It's not squared, it's just regular L. So these are the final answers. This line is a little crooked, but it's okay, because we got the answers. That's all that matters. So cool. That is V2, Phi1, Phi2, pretty much all your remaining unknowns on these two vectors. Okay. Now let's go ahead and do the shear moment, well, shear and bending moment diagrams. Just real quick before we do the shear and bending, just wanted to verify well, not verify, right? Just something you could see. Thankfully, this problem is pretty simple, so you could see it. But you can kind of verify these two answers right here. I've discussed this in other videos and other chapters, but here in this case, right, I mean, if you're applying a force P down here, right, going down with a magnitude P, in this case, right, since these are over 16, let's just assume this is a, well, not assume, but it is a 16 over 16 P, right? It's one P value. That means you have to have a total of one P value going up at your two supports right here, okay? Pretty much going in the up direction. So in this case, F1y, we got 5 over 16 and then 11 over 16. So when you add F1y going up and F3y going up, you do get 5 plus 11 is 16 over 16. Now, with moments, it's a little, I mean, I don't even think you could just visually, right? But I guess that's a cool way to verify at least a couple answers on your final answer list. I don't know. But just wanted to point that out. So let's go ahead and do the shear and bending. I don't even know why they make us do this. I mean, I get it, right? But it's this is more of a statics thing. But I mean, shit, even then, I still mess up. So I guess it's good that they make us do this stuff, right? All right, so in this case, this is what our beam looks like, just rough layout. We're fixed here. There's a force P right at the center. And it's a little hard doing the bending and shear diagrams for these types of problems when they don't give you values. So let's go ahead and assume, right, just to make it easy on us, that L over 2, let's assume this whole beam is 2 meters long, right? In this case, this is 1 meter, and this is 1 meter. Just assume, right? Let's assume P is, I don't know, 1. Let's assume P is 1, just to keep it simple. So in this case, we know F1y for the shear, right? Shear. And this is bending. Okay, so we start off. We know this is the very center of the beam, so let's go ahead and divide that right there. And this is the very edge, right? And it's right there. Whatever, it's not the best. F1y at the very start, we have a force pushing up, right? So that's going to push us up 5 over 16. So it's going to push us up to here, 5 over 16. So we're right here. Nothing happens, nothing happens, nothing happens, nothing happens until the very center. We have the force P, remember? So P is going to bring us down a full 16 over 16. So that's going to bring us all the way down to, let me try to draw it to scale. This is negative 11 over 16. Because we went from 5 over 16, subtract 16 from it, you're going down all the way to negative 11, right? So cool, we go all the way down. Then nothing happens, nothing happens, nothing happens until we finally get to the edge. We have F3y pushing up, right? This was F1, F3. Guess what's going on? So we finally get to 0. So cool. This is our shear. And now we do the moment. So like I said, there's so many ways to do shear and bending. This is how I do it. This is how I was taught. It's pretty much, you do integrals at this point, right? So what you do is you get the area. I said this was 1 meter for simplicity. This is 1 meter in length, right? From here to here, from here to here. So in this case, we do 5 over 16, our height. It's the area of a rectangle. 5 over 16 times 1, base times height. You get 5 over 16, and it's in the positive region. It's above the x-axis, right? So it's a positive. So that means what we do is we start from here, 0, and we have a slope, a positive slope of 5 over 16. So we go all the way here. And that is like this. Oh, not the best. Shit. Whatever. You get the point, right? 5 over 16. So again, this value, 5 over 16, I don't know, right? 5 over 16, and this is, let's assume Newton meters. Oh yeah, Newton meters. Let's assume P is in newtons, okay? I'm just trying to keep it simple for you guys. So yeah, that's pretty much it, right? You have a positive slope of 5 over 16, so you go up, starting from 0, all the way up here. Boom. Then, what do we got? We have no moments going on here, but at this point, we do have the force. And that's causing an 11 over 16, and it's a negative slope. So we start from here, we go down to a slope of negative 11 over 16. There you go. Then you push back up, and that's pretty much it. This is the bending moment diagram right here. Nothing crazy. Again, I'll do more videos, right? But I'll explain it with numbers. It's even for me, it's a little tricky to explain. But I guess for the sake of your homework, this is the answer, okay? And yeah, that's pretty much it. So this was the first problem we did for bending. Again, these things have no axial effect for a beam. Transverse loading kind of is so huge that axial effects and torsional effects are neglected. And this is really useful when you're actually into structural engineering. If you're going down that route, there's this guy at work, he's just on his stuff about this kind of stuff. And like I said, there's so much more to it, but as we go down, we'll start explaining more in detail. But yeah, that's the top right here. This is the bottom. In case I missed it, I know sometimes I don't have it pointed in the right direction, and that's the very back.